On section 7.5, we're looking at dynamics on inclined planes. Now, so far on chapter 7, everything's been static, everything's been still. If it's static, then we know the thing is in equilibrium and we can balance out the forces and we can think about the moments, clockwise moments equal anti-clockwise moments. Now with dynamics, you might think, okay, this is going to be a lot more complicated then, but actually, we basically know all the techniques we need already. We don't have anything to do with moments. If the thing's moving, then we're not going to worry at the moment about turning forces on it. So all the A-level questions where things are dynamic, we throw moments out the window, so we've only got thinking about forces. If we're thinking about forces, then if it's moving, in this case, we're thinking about inclined planes, so the object's going to be moving in this direction, isn't it, up and down the plane. We don't ever have any questions where things are going this way, kind of going up and down the plane, or sort of going up the plane and then sort of flying off in some direction. Now, I say that, I'm sure that somewhere, if you look hard enough on some obscure exercise, there will be a question where something's going up the plane and then flies off the end and it turns into a SUVAT question because it's then a projectile because it's flying through the air. But on almost every single question I can think of, we are going in this direction. And if we're going in this direction, then in this direction, there's still no acceleration. So, in fact, there's no movement in this direction. It's not going out from the plane, it's not going down into the plane. Therefore, in this direction, we're still in equilibrium and we balance the forces. In this direction, we've got to ask ourselves, are we accelerating? If the thing's moving at a constant speed and there's not an acceleration, then the forces balance out because we're still in equilibrium. If we're accelerating, then we apply F equals ma. But think about how that works with the forces. Forces up the plane equal forces down the plane, that's equilibrium. Forces up the plane take away the forces down the plane equals mass times acceleration. That's acceleration, okay? Now, there's no real difference in the difficulty of those two situations either, is there? You need the forces up the plane, you need the forces down the plane. That's the difficult bit. Which equation do you put them into? Do you put them equal to each other, or do you do one take away the other and put it equal to mass times acceleration? That's the difference, okay? So we already have all the difficult techniques in the bank here. The other thing to bear in mind is friction. If we're moving, doesn't matter whether we're in equilibrium or we are accelerating, there is going to be friction. It is going to be the maximum possible friction, so equal to mu times r, and it is going to be acting in the direction opposite to the direction of movement. So as with the rest of chapter 7, what I'm really going to do here is do the example, but one more thing to say before I do, which is this. A problem with friction is this. You might start off with this object, so let's invent a question, a typical sort of question. This object is sliding down this plane, so if it's moving this way, friction is acting like that. And then you do that and you work out part A of the question, whatever they're asking you to find. And then they say, somebody comes in, and you remember at this point, at the end of part A, you've got a diagram with all sorts of forces thrown in all over the place. I don't know, somebody's trying to stop this moving and it's actually sliding even so and whatever. There's lots of forces and you've done all your angles and all the resolving. Then in part B of the question, they come in and they say, an extra force gets added in and now it starts being pushed up the plane. And the temptation is to leave your diagram and just adjust it a little bit. But of course, that friction force, if we now have an object moving up the plane, the friction force is trying to stop it move and trying to make it go down the plane. So you have to start again, if that's what happens from part A of the question to part B of the question. If it's moving in the opposite direction, you have to start again with the diagram because the friction force is going the other way. You can't just sort of slightly adjust your diagram. You need to take a whole force and remove it and put it in a completely different place. So just bear that one in mind. But really, that's it in a nutshell. We know how to do the difficult stuff because we know how to work out the upwards and downwards components, up the plane and downwards, down the plane components of all the forces involved. The out of the plane and into the plane components of all the forces involved. We just have to put them into a slightly different equation if we have an acceleration going on. So let's have a look at example 9. I suppose the other thing to add in, by the way, folks, is that almost always in a dynamics question, we do have an acceleration going on. It is dynamic if it's moving, but we don't tend to have a thing going at constant speed. We tend to have an acceleration. A particle is held at rest on a rough plane which is inclined to the horizontal at an angle of alpha. So here's my particle, here's my angle of alpha, there's the weight force. It's immediate that we can put in our usual, there must be a reaction force, that angle there is alpha. We do that automatically now, I hope. We're told that tan alpha is 0.75, which I'm going to write as 3/4, and we'll save that information for a minute. The coefficient of friction between the particle and the plane is 0.5. Let's write that one on there in a little circle. We'll say that for later. The particle is released and slides down the plane. Find the acceleration of the particle. So it hasn't told us, well, it's told us that it slides down the plane. So I know that this here is mu times r. There's no extra forces added in, but there is also no information about the mass of this particle or the weight of this particle. So we're just going to have to call it mass m and say it's mass times gravity is my weight force there. Now we know it's sliding down the plane, so it might help to put an acceleration on the diagram there just to remind us that we have an acceleration. So what do we have? In the same way as if we had a statics question, we're going to think in this direction, we're going to think in this direction. So instead of thinking, oh, well, I'm resolving forces or I'm applying efforts, I may just think, well, we do this direction and we do this direction. It's the same thing. So these questions really, in my head, aren't any different to the statics questions. So in this direction, is there any acceleration? No, there isn't. So we're going to resolve the forces, balance them out. Forces out from the plane, that's just r. This one is not pushing out, it's not pushing in. This one here has a component which is pushing in. That component is mg cos alpha. If you're not happy doing that quickly, then perhaps go back through the playlist and watch some of the examples from earlier in the chapter, because by now this is routine stuff. That's not saying it's easy, it's just saying that we've practiced it enough for it to become routine. Apologies for the slightly clunky edit on the parallel to the plane part. I just made a mistake, so I'm just going to do this bit again. So going in this direction, parallel to the plane, there is an acceleration, so we're applying F equals ma. Down the plane, I've got this force mg sine alpha. That's the down the plane component of this force. Then pushing back up the plane, I've got mu r, so that's take away mu times r, and this force doesn't push up the plane or down the plane. So mg sine alpha take away mu r, and then we have that is equal to mass times acceleration, so the mass is m and the acceleration is a. Now we have equation 1 and we have equation 2. We are trying to find the acceleration and we're trying to find the distance it slides off the first 2 seconds. Well, the acceleration, that's a. So can I find that from these equations? Let's have a look at them. I've got an r here and I can substitute into this equation for r. And then what would I have? I've got an alpha. Well, I can find alpha, or specifically I can find sine alpha and cos alpha because I have the information there. I've got a mu and I know what mu is. So from these two equations, what's missing? I've got a, m and r, and if you remember, when there's an m flying around, often it helps just not to worry about it. So I'm going to substitute equation 1 into equation 2, and that's going to give me that mg sine alpha minus mu times mg cos alpha equals m times a, and now I can divide everything through by m, and that problem's disappeared. What have I got? I've got a in terms of mu, which I know, sine alpha and cos alpha, which I can work out, and g. So there we go. All right. In terms of working out sine alpha and cos alpha, by the way to do it would be this, I would suggest. Tan alpha is 3/4, so imagine a little right angle triangle. Opposite over adjacent is in the ratio 3 to 4. So that would mean this one would be 5. So sine alpha is 3/5, cos alpha is 4/5. So that is g times 3/5 minus mu is a half, times 4/5 times g equals a, and that allows us to have an exact a as an exact multiple of g, which is helpful if we're then going to use it later on. We might not want to round it earlier on. 0.2 g. I'm cheating slightly and just taking that out of the textbook instead of doing all the fraction calculations. Okay, so we have that. Now, so far, that is really, I think, the same as a statics question. I know we had to apply F equals ma instead of resolving forces here, but really, it was the same technique, wasn't it? It was that, take away that. The difficult bit was finding this and this. The next part, find the distance it slides in the first 2 seconds. Well, in this case, u, v, a, s, t. I know that the acceleration is constant because it says so. The initial velocity is 0 because in the question it says we start from rest. I'm taking the positive direction as down the plane, so there's my acceleration. S is the distance that I want, t is the first 2 seconds, so t is 2, and I don't care about velocity. So we can apply the Suvat equations. Those are the bits of information that I know. s equals ut plus a half at squared. Okay, now there's another example of something we've seen a lot all the way through the A-level syllabus. Once we know some information from two different areas, we can combine those two different areas into one question. And there is an example of how we've done it there. Now I'm going to do example 10 from page 148 because there's no reason not to. If you don't feel like you need this example, then you can carry on yourself with the exercise. I think the real lesson to learn from this one, though, is it doesn't matter what they're asking us for this time is to find the coefficient of friction and the acceleration. It doesn't matter what they're asking us for, the method that we're going to use is the same. So we read the question, we kind of ignore what they're asking us, we go through all the same motions, and then we go back to what are they asking us. So we've got a box of mass 2 kilograms. I'm modelling it as a particle, so I'm just drawing a little circle. In the book, they've drawn it as a little rectangle. I'm just going to leave it like that. So it's 2g is my force. I know that it's hard, there we go. It is being pushed up a rough plane by a horizontal force of magnitude 25. So there is my horizontal force of magnitude 25. I like to put my forces on starting at the object and moving from there. So it looks different again to the book, but that's the way that makes it clearer in my head. Obviously somebody couldn't be inside this, you know, inside the ground pushing this thing up the slope. But if I imagine an imaginary string sort of inside the ground, it has the same effect as somebody pushing here. So I draw my forces like that. It's being pushed up the slope, so it is overcoming this friction. It's moving, so this is mu times r, and of course I got my usual r reaction force on there. The plane is inclined to the horizontal at an angle of 10 degrees. As in previous questions, I've not made any effort to make my 10 degrees look like 10 degrees. I've just drawn it about this big, so there's room on the diagram for everything. If you prefer your angles to be closer to the angle they're supposed to be, then you can draw your diagrams that way. Given the coefficient of friction between the box and the plane is 0.3, sorry, so they give us mu, they're not asking us to find it, but they could be asking us to find it, it doesn't really matter. They want the acceleration of the box. So what do we have? Well, we have in the perpendicular to the plane direction, as we almost always do, we're resolving forces, we're balancing the forces out. It might help to just have the fact that this is 10 degrees and this here is going to be 80 degrees because that's vertical, that's horizontal, this thing is 90, that bit of it there is 10 degrees. So, pushing out from the plane is r. Going into the plane, we've got 2g sine 10 degrees, and we've got the into the plane component of this 25 Newton force, so that is, 25 cos 80 degrees. So if you like, that part of the force here is wasted, isn't it? We just, that effort is spent pushing into the plane and not pushing the thing up the plane at all. So there's equation number one. Up and down the plane, we know we are accelerating, so we're going to apply F equals ma. And we're going this way. We have this plane, this force here provides an up the plane component of 25 cos 10. Or if you prefer 25 sine 80. Down the plane I have, take away 2g sine 10 degrees from this force here. And we've got a mu r going down the plane as well. That equals the mass, which is 2 kilograms, times the acceleration, which is a. There's equation number 2. Looking at these two things, what have we got? We've got two equations. R, I know. There's nothing in there that I don't know. I can work out sine of 10, I can work out cos of 80. We know what g is, so that's good. In this equation, I've got a. There's an r, which I can substitute in from equation number 1. There's a mu, which I know is 0.3, so we can put that in there. Everything in this part of the expression I know. Everything over here I know. So we can work out the acceleration by simplifying equation 1 and substituting it in, taking mu equals 0.3 and substituting that in. And that should get us to the answer. Okay, that's the end of section 7.5.